So we're going to do random variables, discrete probability distributions. We're going to talk about what is an expected value in a variance. It's very similar to a mean and a variance that we learned before. But now we have to worry about weights being different than just 1 over n, meaning that the x's have different likelihood of showing up, not like before where we just took the numbers, added them up, and divided by the number of observations we had. The 3 types of discrete distributions we're going to talk about are binomial, Poisson, and hypergeometric. The binomial is one that's used quite often to do things where it's a yes or no answer. So, did you pass the class? Did you not? Did you buy a bike? Did you not? Those types of questions. A Poisson is used to do count variables. So, how many cars go through an intersection? How many people graduate in a year? Right. When you want whole numbers to matter, a Poisson is a very good distribution. And then hypergeometric is one where you are worried about replacement. Right? You are worried about someone going in and picking the same number. So first let's talk about what a random variable is. A numerical description of an outcome of an experiment. So this is the thing that you're interested in. The thing that you have an idea about what you're trying to measure. That is the random variable. The only reason it's interesting is because it has different values to it. If it had the same value every time, there'd be no point in doing the experiment. Right? But this is the thing that we're interested in. Now these random variables, they can either follow a normal distribution, they can follow a binomial distribution, a Poisson, an exponential, all different types of distributions. And we're going to try to see how they behave given these distributions. Now for our purposes, we're going to separate up a random variable into 2 categories. One is discrete and the other one is continuous. A discrete random variable can only hold whole numbers. It can also only hold a finite amount of numbers. Right, so it can't be infinite. A continuous random variable, kind of by its name, can hold any value. It can even be limited between 0 and 1, but it can hold any value between 0 and 1, which means it has an infinite set of values, even between 0 and 1. We can make it between 0 and a half. Still, there's an infinite number of values between those 2 points. So a continuous variable can hold any of those values. This distinction is going to be very important. For a discrete probability, usually every point has its own likelihood of occurring. Right, so it's very easy to calculate the probability. It's kind of like we did in the previous section. Right, we could say, what is the probability of being discovered? What is the probability of having a locator? Very discrete, finite category. For a continuous random variable, it's not as easy. In fact, there is no probability for one distinct point, and we'll see why that's true later on. All right. So the discrete random variable may assume either a finite number of values or an infinite sequence of values, but it has to be whole numbers. Whole numbers, 1, 2, 3, 4, 5. It has to be whole values. Continuous random variable may assume any numerical value in an interval or collection of intervals. So things like number of TV sets you sold, number of laps you did in the pool, as long as you completed your lap, number of sets you did in the gym, number of classes you took, number of cars you own, number of homes you have, number of bedrooms you have, all these things where half is not part of it. So we're going to let x be the number of consumers arriving in one day, where x can take on the value of 0, 1, or 2. We can count the customers arriving, but there is no finite upper limit to the number that might arrive. So then this leads us to the probability distribution. Now, up until this point, we've made some assumptions about general distributions. For example, if you get to see every observation in a sample space, and you add them all up, the probability of all those events, what should it equal? 1. So that's one rule that's going to continue throughout. Now, how we calculate up to 1 is going to be different depending if it's discrete or if it's continuous. If it's discrete, it's going to be very similar to what we previously did. You just add up what those probabilities are, and they should always sum up to 1. In order for an observation to exist in our distribution, we're going to be using this term f of x here. F of x represents the probability of x occurring. Let me say that one more time since we're going to be using that f of x a lot. This lowercase f of x represents the probability of that point occurring. We're also going to use an uppercase version of that. The uppercase version of that is a cumulative probability of that x occurring. So being equal to x or less than. Now that particular x exists in our data so long as this thing is positive. Right? If f of x is equal to 0, that means that x will never occur. When we sum up all the probabilities, they have to equal 1. And that's just to be consistent with the idea of having full sample space. They have to equal 1. So here's one example. We have units sold, number of days, and then we have our x values. So we have 80 days where 0 units were sold. We had 50 days where 1 unit was sold, 40 days where 2 units were sold, 10 days where 3 units were sold, and 20 days where 4 units were sold. What we're going to do next is we're going to make a relative frequency table, meaning that we're going to take that total, 200 days, and we're going to find out what is the likelihood of x occurring. So if we have 200, and we have 80 divided by 200, we get a probability of 0.4. Right, so 40% of the time we have 0 units sold. Not very good for business. Do the same thing here with 50 and 200. Divide those two, we get 25%. So 25% of the time you sell 1 unit. Do the same thing for 40 over 200, you get 20%. 10 over 200, you get 5%. And 20 over 200 again, you get, 20 over 200, you get 10%. They should sum up to 1, and they do. And the next thing you should notice is that they have different weights associated with them. So if we want to find out what is the mean for this distribution, it's not just summing up 0 to 4 and dividing by the number of observations we have, which would be 5, right? That's not enough. We actually have to weight the mean now. So in order to do an expectation here, you're going to take 0 times its probability. 1 times its probability. 2 times its probability. All the way down. The way to think about it is that the general formula for a mean is the sum of x times its probability of x. Now let's think about what that meant before. If everything had the same likelihood of occurring, and we had n observations, then f of x would equal 1 over n for all of our observations, right? We had n things and they all have the same likelihood of occurring, then the likelihood any one of them would occur would be 1 over n. If that's true, we can replace that in here. We have the sum of x times 1 over n. 1 over n is a constant, so since it's a constant, we can pull it out. Here what I'm telling you now, in these new discrete distributions, is that they don't all have the same probability. They have different ones. So we're going to have to follow this rule. So different ways that we can represent these probability distributions. One is that you can use a graph where on the y-axis you have the probability, or essentially the relative frequency. And on the x-axis you have the values. You'll notice that we have these columns coming off of each one of those values. You can think of these as the probability mass, the probability space that's belonging to each one of those observations. The first type of distribution we're going to talk about is the basic one, the uniform distribution. Every observation has the same likelihood of occurring. So f of x is going to equal 1 over n for all of our x's. And this is just our straight mean that we had before. The way we calculate the variance is the same. The way we calculate standard deviation is the same. All those formulas you have on your formula sheet up at the top, they all apply to the uniform distribution. We're going to calculate the mean and the variance for these distributions. The mean is going to be equal to the x that you observe times its probability over all of the observable x's. If it's just a uniform distribution, it's this guy right here. If it's something other than a uniform distribution, then you have to find the probability for each one of those x's, multiply times the x, and then sum them up. The same thing is true for the variance. The variance, I told you before, was the average squared deviation, right? So we're always dividing through by n, if it was the population, or n minus 1 if it was the same. Now, if they have different weights associated with them, we have to weight each one of those deviations. Those that are most likely to occur should have a bigger influence on the variance. Those that are much less likely to occur should have a smaller influence on the variance. So we have to weight each one of those observations by its probability. And the standard deviation is still the same. Take the square root of the variance. Alright, so if we go back to our example with the TVs, we're going to go ahead and multiply across. We have x times 0.4, it's easy math, 0. We do it again for 1 times 0.25, 2 times 0.2, 3 times 0.05, and 4 times 0.10. Okay? We sum them down, and that gives us our expected value. So the expected number of TVs you would think you would sell on any random day is 1.2. Now the reason this works is that if we did it right, and we sum up all f of x, it should still equal 1. If it doesn't, that means we screwed up somewhere. Right? It means we left an observation out. The same thing we're going to do for the variance. We're going to use the same chart we did before for the variance. Remember how I separated up into columns for you? Right, we find the mean. The mean was 1.2. We subtract it from the x. We square it. We again hit it by its probability. And then we multiply it through. So the only new step you're doing from the previous section is that you have to include this column and this column. Everything else is the same. Now, if you have a very large data set and you need to do this a bit quicker, you can do this using Excel. Excel can still do the sum of the products. It has a special function for that. So you only have to put in the row one time. And what it's going to do is when you put in the sum of the products, it's going to take what is the first column you're going to have in that product, what is the second column you're going to have in that product, and it's going to multiply across first and then add them, going down. So in other words, it's going to do this step going here to here, here to here, here to here, here to here, and then adding those products together. You could also do it in pieces on the side. So again, we get the mean is equal to 1.2, variance equal to 1.66, and the square root of that gives us 1.2884. Now here's the new one. This is one you haven't seen before. This one's going to include the combination rule. Right, this is a binomial distribution. Here you only have two outcomes, either a success or a failure, meaning that the event either happened or did not happen. This doesn't work for things that have multiple outcomes to them. So did you pass the test? That works. Not, what color is your car? That doesn't work. Right? Unless you want to say black or not black, white or not white. These only work for success and failures. The way we work these is that there has to be a probability of success, P, and there has to be a set number of experiments, if you will, that you're going to run. Now, each one of these experiments have to be independent from one another, meaning that whatever happened before doesn't influence what happens today or what happens tomorrow. So here's one example. Evans is concerned about a low retention rate for employees. On the basis of past experience, management has seen a turnover rate of 10%. So that's our probability of success here, if you will. Thus, for any hourly employee chosen at random, management estimates a probability of 0.1 that the person will not be with the company next year. So here, our P is going to equal 0.1. They're going to choose 3 hourly employees at random. What is the probability that one of them will leave the company this year? So here, the total number of experiments we have is 3. The total number of successes that we have is 1. So how many different combinations can we have where we have big N is 3, and number of successes, or in this case, little n, is 1. So that's what we're going to have as the first part of our combinations. Right? We need to know the total number of possible combinations we have. The second part tells us what is the likelihood of that combination occurring given a probability. So what is the likelihood of having one person leave, or x will be equal to 1 here, and 2 people stay? So 1 minus p are people who are staying, right? 10% of people leave, so 90% of people will stay. And we want 2 of them to stay. So the n minus k up here. 3 experiments, 1 person leaves. Now the order doesn't matter, right? We don't care who leaves. Just that it's 1 that leaves. So this should be new to everyone. If not, then hopefully you're going to have a real easy class the rest of the semester. This is a binomial distribution. This is what was used before we could actually have computers to work out a normal distribution. Because this you can do by hand. So in our experiment, we'd have 3, choose 1. We'd have 1, success, in this case someone leaving, and 2 failures. Failures happen 90% of the time. And then we just put that in our calculator and go. We find that there is a 24% chance that someone would actually leave the company out of those 3. You can use binomial tables if you had to in order to do this. Luckily, we live in the era of computers, so hopefully you'll never have to use the table again. But if you had a table, you would have to go to the specific table where you have number of successes, another one that tells you how many experiments occurred, and what the probability would be. And then you can go inside of that table to find the actual probability. So, for example, we have 1 success. Our P was 10%. Where those 2 meet, give us the probability of that previous function. In Excel has all these distributions put inside there. In Excel, you're going to have your binomial distribution. You're going to have the first column be the number of successes that you have. You're going to have the second item be the number of trials. And the third item is going to be the probability of success. This last part here where you see false, this last part says I only want the probability of that specific event. If you put true instead, it tells you what is the probability of being, say in this case, 0 or less than 0. So it gives you the cumulative probability. And this is consistent now. I checked it recently with the old Microsoft Excel and the new one. The new one has this option as well as an additional option, but it kept the legacy version of it to be consistent. You need false here in order to make sure you get the probability of just x equaling 0. If you put in true, then it tells you the probability of x equaling 0 or less than 0. So here are our total numbers. They should sum up to 1 because we're looking at all of the possible outcomes in our sample. Notice that 0 is part of our sample, right? You can have no one leave. That's a possibility. You can also have everyone leave. That's a possibility. It's unlikely, but it's possible. Now, the other thing that we're going to do in these setups are ask questions like, what is the likelihood of 2 or more employees leaving? Right, we can answer that question using the cumulative distribution. What is the likelihood of 2 or more employees leaving? So let's go back to the formula to see how we would answer that question. If I said 2 or more, you'd have to either find the probability that 2 people leave plus the probability that 3 people leave. You can do it that way. Or you can do the opposite. What is the probability that no one leaves? What is the probability that 1 person leaves? Add those 2 up and subtract it from 1. Because whatever's left over has to be greater than that amount. In those cases, you want to use that cumulative property. In particular, if the numbers get really large. Right? As the numbers get larger, it's a lot of things to calculate. So one of the questions that I like to ask, and anyone who has exams love to ask, is they'll give you something like, we're going to have 10 experiments. We want to know what is the likelihood of 1 or more people leaving the company. So you could try to follow it the hard way. You just do it for 1, then do it for 2, then do it for 3, then do it for 4. Or you can do it the easy way, remembering the law of probability that it has to sum up to 1, and just find what is likely that no one leaves. And then take that from 1. If you have the probability of no one leaving, you subtract that from 1, that's the probability of someone leaving. Could be 1, could be 2, could be 3, could be 4. They love to ask that question. I would be very surprised, especially if Aptly doesn't ask you that question. So there is our cumulative probability. You can see as we go down and get towards the highest value, we get all the way up to 1. For the binomial, the expected value is actually quite simple. You take the number of trials you have, and you multiply it times the probability of a success. Now the reason this works out intuitively is that each trial is supposed to be independent, right? If each trial is supposed to be independent, that means it's a flip of a coin every time, or an unfair coin according to the probability. The variance actually has a neat way of calculating it. You don't have to do all this extra work to calculate the variance. Right? Before we were doing x minus its mean, squaring it, and adding it to the next one, to the next one, to the next one. This one has a nice little property where you just take that original p and you multiply it times its opposite. I'm going to get n times p for the mean, and I'm going to get n times p minus 1 minus p for the variance. And standard deviation is still the square root. So for the binomial distribution, we can find the expected number of employees to leave if 10% of them leave and we have 3 experiments, which is going to be 0.1 times 3. We can find the variance rather quickly. We're going to have the 0.1 times 1 minus 0.1, which is 0.9. We'll multiply that times 3, which gives us 0.27. And then we can take the square root of 0.27 and find that the standard deviation is about half of an employee. All right, this would be... No, I still got a couple minutes. So we're going to do the Poisson distribution, and we'll stop right after that. For the Poisson distribution, this is the number of occurrences within a finite amount of time. So how many cars go through an intersection within an hour? How many animals cross the highway within an hour? Things like that. The probability of an occurrence is the same for any 2 intervals of equal length. The occurrence or non-occurrence in any interval is independent of the occurrence or non-occurrence in any other interval. So this is only useful when you're comparing apples to apples. In other words, you can't use this to find the number of cars that are on I-64 on Monday at 8 o'clock versus Sunday at 3 a.m. And those are not the same time intervals. That would not work. They have to be at least similar enough in order for you to be able to use this. Okay, this one also has a funky looking probability distribution to it. There's that factorial popping up down in the denominator. You are given mu, so you're told what the population mean is. And then x here is still the number of successes, meaning how many cars did travel through the intersection. Now the funny thing about the Poisson distribution is that its mean and its variance are the same. It's a very weird property. Mean and its variance are the same. Alright, so here's one example. Patients arrive at the emergency room of Mercy Hospital at the average rate of 6 per hour on a weekend evening. What is the probability of 4 arrivals in 30 minutes on a weekend? Well, we know that mu is 6 per hour, and in this case we need to make it into half an hour. Divide that by 3. Sorry, by 2 to make it 3. So here is our mu. We want to know what is the likelihood of 4 successes. So x is equal to 4. This is the exponent. You're going to have to put that in, not by hand, just use the little b on your calculator. This again here is the mean. And there is your factorial for x. So we get about 16.8% chance that there are 4 arrivals in 30 minutes. For the Poisson in Excel, again, you would follow the same format as the binomial, where you have the Poisson. The first value is the number of successes you have. The second value is the mean. Right? So this is up here at A1. And then the last value you want false if all you want is the density function, so just the mass itself for that one point. You want true if you want that value or less. Right, so false is the probability density function. True is the cumulative density function. Let me say that one more time. This is going to be true when we do continuous distributions as well. All right, false is for the exact point. True is for the cumulative. So anything that's that value or less. So here you see that the Poisson distribution does have a bit of a bell shape to it. As you get closer to the mean, you get a higher probability. As you go farther away from the mean, you get smaller probabilities. If we replace all those false with trues, it gives us the likelihood of 0 or less, of 1 or less, of 2 or less, so forth. So all those should sum up to 1. The Poisson doesn't go all the way up to 1 in this case, only because you don't know how many people can show up, right? You can have 100 people show up. It's very unlikely, but you can have that. So we can continue to add numbers to this one if we wanted to. So it's similar to the binomial in the sense that we use 2 sets of count variables. All right, so we're looking at counts. The difference is that instead of just treating everything the same, we can actually split it up into parts. We can say we're only interested in a subsample within there. So these are used for questions where you have, let's say, an urn full of balls with different colors. Right? Say that we have red and green balls inside of an urn. And I want to know what is the likelihood of you grabbing 2 red balls and 1 green ball, given that there are a total number of 64 balls in the urn. Something like that. The fact that I have 2 subsamples within the larger sample makes it that we can't use the binomial anymore. So we need something new. This new thing is the hypergeometric. It allows us to separate up into subsamples. So this is what it looks like. It's a full combination in the denominator, and then the 2 separate samples in the numerator. Right? So going back to my question about the urn and having these red and these green balls, what you'd have is you'd have one set of R green balls, and then whatever's left over has to be our red balls. Okay? And then from each one, I can either choose all from just green, all from just red, or a mix between the 2. Okay? And then in the denominator, I have to have all combinations of choosing any one of those balls. So what we have here is we have a larger group, this big N, represents all of the elements, all of the balls that are inside the urn. From there, I'm going to pick, say, 5 balls, and I want so many of them to be successes, meaning that so many of them have to come from a particular group. Now this part up here, you already know this is just a combination multiplied by another combination divided by an even larger combination. Let's do an example to kind of make it more concrete. Bob Never Ready has removed 2 dead batteries from a flashlight and inadvertently mingles them with the 2 good batteries he intended as replacements. The 4 batteries look identical. Bob now has randomly selected 2 of the 4 batteries. What is the probability he selects the 2 good batteries? So here we have a sample of 4 batteries, right? My problem is 2 are good and 2 are bad, so they have subsamples. Think of that as being the red and the green. Right? So we can use the hypergeometric to figure out what is the likelihood that he actually picked. So in this case, the total number of batteries we have, our big N here is 4. Total number of batteries that we're choosing is 2. And the total number of good batteries that exist is also equal to 2. Alright, we have 2 good batteries. We're choosing 2 from the possible 4. We need to figure out, well, what's the likelihood that we actually choose 2 good ones. So let's put this as good up here, bad over here, and down here is total. I have 4, choose 2. So those are all the possible combinations of me choosing any one of those 2 batteries, right? Regardless if they're good or bad. From here, I have 2 good batteries, and I'm going to try to choose both of those good batteries. And over here, I have 2 bad batteries, and I'm hoping to choose none of those. So I want to know, what is the likelihood of me choosing 2 batteries at random that they're both good? So I can do this combination. Figure it out. When I plug it in, I have 2 over 2 here for the first combination, and 2 over 0 for the second combination. That's going to give me 2 factorial over 2 factorial. It's going to cancel out for, there's a line between here that come out as well. And then I have 2 factorial again over 2 factorial. It's going to cancel out for us. This is really 1 times 1 here. And then down in the denominator, we have 4 factorial divided by 2 factorial, 2 factorial. So if you break that down in your head, it says 4 times 3 times 2 times 1. In the denominator, we have 2 times 1 and 2 times 1. And we can knock off 2 times 1 in the numerator and still have 4 times 3. 4 times 3 is going to be 12, divided by 2 is 6. So we have 1/6 or 0.167. So in Excel, The way you can do this, you can use a hypergeometric distribution. Again, across all the Excels, they have this old function. They have some new ones to go along with it. If you use the new one, you want the one that says dot this to it. If you use the old one, it's exactly this one, and it exists in the newest version of Excel as well as the 97. When you enter it into the function, your first value is the number of successes you have. So this is, in our case, the first two, right? Pulling two good batteries. The second one is the total number of pulls you have, which in our case is still 2 because we're only pulling 2. The third one is the total number of possible successes, so the 2 good batteries that exist in the population. And then the last one is just the total sample space, so all values that exist inside of that Earth. If we do that, again we get the 0.1667. Alright, so here's your problem. You have a wallet containing 3 $100 bills, and it also contains 5 $1 bills. So in total, how many bills do we have? Good. So we're all on the same page. You're going to randomly choose 4 bills from that wallet. What is the probability that you choose exactly 2 $100 bills? Which means how many $1 bills do you have? You're choosing 4, right? So if you have exactly 2 $100 bills, how many $1 bills do you have? 2. Make sure you have that set up in your combination. Go ahead and try that, and then I'll walk you through it. Alright. So now I was hoping we'd have more people in the classroom, which means I'm probably going to fail on this one. But there is a problem that you can do using either hypergeometric or just straight probabilities in order to figure out whether or not someone shares a birthday in a row. Now, you would think that that's something really hard, right? Because there are 365 days a year, and sure, maybe there are certain months that are more popular than others for birthdays, but it would still seem odd that with just 23 people, you have a 50% chance that someone shares a birthday. Maybe not you, but someone else in the room might share a birthday in the class, right? So, let me show you why. Hopefully I have this set up.
Okay, so today we've got exclusive access to Nottingham Forest football ground here. 2-time European Cup winners who have given us the access so that we can talk about a very important number in football and a very important number in probability, which is the number 23. Okay, so 23. So why is 23 an important number in football? Some of you may know this already. That's the number of people that you will have on the pitch during the game. That's 2 teams of 11 and the referee. So there are 23 people on the pitch. Now, here's my question today. What's the probability that 2 of those people will share a birthday? The answer may surprise you. So we're not talking about the year, we're just talking about the date itself. Maybe it's the 14th of January, maybe it's the 5th of June. We're talking about the date itself. So let's work this out. I can make this slightly easier if I ask the opposite question. I'm going to work out the opposite, which is what's the probability that no one on that pitch shares a birthday? That's an easier question to answer. Let's do this. Okay, so your first player, okay, it doesn't matter what birthday he has, but when your second player gets on the pitch, what's the probability that he doesn't share a birthday? Well, he will have, out of the 365 days to choose from, he can have a birthday on 364 of them, out of 365. So we're not including February the 29th, no leap years here, and we are assuming that all days are equally likely. Okay, so your second player has to have one of these days. Your third player, when he comes onto the pitch, will have a choice of 363 days out of 365. And then what next? The fourth player. Out of those remaining days, he will have 362 out of 365. And you can keep going. Eventually, you'll get to the 23rd player. That's called the referee. So your 23rd player, how many choices does he have? He will eventually get 343 days left out of 365. So this is the number of days that you're allowed to have for that referee's birthday, because we are looking at no one sharing a birthday. Now, if you want to find out the probability that no one shares a birthday, you multiply all these together, and you'll get a number. And that number is round about 0.493. If you're not happy with probabilities like that, that's 49.3%. Just slightly under half. We were interested in the opposite question. The opposite question was the probability that someone does share a birthday. That's the opposite thing of what we've worked out. So, the probability that someone does share a birthday will be 50.7%. It's slightly over a half. You're more likely for two players to share a birthday than if they don't share a birthday. And that's quite surprising. And people wonder, think, well, it must be something like 100 people. You must need 100 people for that to be true, or 200 people. If you think of it this way, think of all the pairs of people you can make out of 23 people on the pitch. All the possible pairs of people. In fact, there are 253 pairs of people you can make. And, well, think of it that way. You can start to see why it's quite likely that two of those people will share a birthday. So next time you're at a football match, think of it. There is you have a greater than 50% chance that two of those people share a birthday.